What if everything you thought you knew about reality was just the tip of an iceberg? Imagine a universe not just with the familiar dimensions of length, width, height, and time, but infinitely more. We're diving deep into the mind-bending concept of hidden dimensions, a secret layer to our cosmos that could explain everything from dark matter to the very fabric of existence. Get ready to have your perspective shattered. For centuries, humanity has looked to the stars, studied the intricacies of nature, and sought to understand the very nature of the universe. We've uncovered the 4 dimensions of space-time that govern our existence: length, width, height, and time. But what if these dimensions are just the surface of a much deeper and far more complex reality? The possibility that hidden dimensions exist beyond our perception is one of the most mind-bending concepts in modern physics. It challenges everything we thought we knew about the fabric of the cosmos. From string theory to supersymmetry, scientists are exploring theories that suggest that our universe may be far stranger than we can imagine. In fact, the reality we experience may be just the tip of the iceberg. Beneath the familiar world of atoms, galaxies, and stars, a secret layer of dimensions might lie waiting to be discovered. This hidden layer could explain some of the most profound mysteries of the universe, from the strange nature of dark matter to the very essence of existence itself. But before we dive deep into these secrets, let's start with the foundation: how theoretical physics has begun to uncover the existence of these hidden dimensions. Whispers of the unseen. Theoretical foundations. To understand the profound implications of hidden dimensions, we need to dive deep into the theoretical foundations that suggest these dimensions may exist. These concepts, though abstract, have become central to the most advanced theories in modern physics, particularly string theory, M-theory, Kaluza-Klein theory, and supersymmetry. These ideas form the bedrock of our understanding of a universe that stretches far beyond the 4 familiar dimensions of space-time. Let's explore these theories and how they hint at the existence of dimensions that are beyond our current perception. String theory and M-theory. At the heart of modern theoretical physics is the idea that the universe is fundamentally composed of tiny, vibrating strings rather than particles. This revolutionary concept is encapsulated in string theory. In string theory, all fundamental particles from electrons to quarks are not point-like objects, as we once believed, but rather tiny, oscillating strings of energy. These strings vibrate at different frequencies, giving rise to the various particles we observe. One of the most fascinating aspects of string theory is that it requires the existence of extra dimensions. In the version of string theory that is most commonly studied, called superstring theory, it is proposed that our universe doesn't have just the 4 familiar dimensions of space-time. Instead, it may have as many as 10 dimensions. 9 of these would be spatial dimensions, and 1 would be time. But here's the kicker. Many of these extra dimensions are thought to be compactified, meaning they are curled up so small that we can't perceive them. These dimensions exist on scales far smaller than the Planck length, a minuscule scale of about 10, -35 meters, which is far beyond our ability to measure with current technology. Despite being hidden from view, these extra dimensions may influence the physical laws we observe in our everyday world. They could explain some of the universe's most perplexing mysteries, such as the weakness of gravity compared to other forces, and why the constants of nature seem so perfectly fine-tuned for life. M-theory, which is an extension of string theory, further refines this idea by proposing that the fundamental building blocks of the universe are not one-dimensional strings but higher-dimensional objects known as brains. In M-theory, these brains can exist in multiple dimensions, and our entire universe might exist on one such brain, embedded within a higher dimensional space. This opens up the possibility of a multi-dimensional universe, with other brains potentially hosting parallel universes that are completely separate from our own. Kaluza-Klein theory. Electromagnetism as a curled-up dimension. The concept of hidden dimensions isn't new. The origins of this idea can be traced back to a 1919 theory by Theodore Kaluza and later developed by Oscar Klein. Kaluza-Klein theory suggested that electromagnetism, the force responsible for electricity and magnetism, could be explained by a 5th dimension. This theory was groundbreaking because, for the first time, It proposed that gravity and electromagnetism could be unified as two manifestations of the same, a fundamental force, a concept that was a precursor to modern attempts at unifying all fundamental forces. In the Kaluza-Klein theory, the fifth dimension is compactified, much like the extra dimensions in string theory. This means that, although it is theoretically present, it is so small and tightly curled up that we cannot observe it in our everyday experiences. The theory proposed that the electromagnetic field could be described as a manifestation of the geometry of this extra dimension. The force of electromagnetism, then, is not a separate force from gravity, but instead a force that emerges from the structure of higher dimensional space. Though Kaluza-Klein theory has largely been superseded by more advanced models like string theory, it was an important stepping stone that introduced the idea that our familiar forces might have deeper connections that require hidden dimensions to explain. The idea that an additional dimension could explain electromagnetism suggests that there could be many more dimensions waiting to be discovered, each potentially responsible for different forces and particles in our universe. Supersymmetry and the search for new particles. One of the most exciting aspects of modern physics is the search for new particles that could confirm the existence of hidden dimensions. One of the theories that holds great promise in this regard is supersymmetry. Supersymmetry posits that every particle in the standard model of particle physics has a superpartner, a particle that differs in its spin but is otherwise similar in other respects. Supersymmetry suggests that there are more particles than the ones we currently observe. For example, the electron would have a superpartner called the selectron, and the photon, the particle that carries light, would have a superpartner called the photino. These supersymmetric particles have yet to be detected in experiments, but their discovery would be a huge step toward confirming the theory. What does this have to do with hidden dimensions? Supersymmetry is closely linked to string theory and the existence of extra dimensions. In supersymmetry, the superpartners of particles arise from the properties of these hidden dimensions. The interactions between these superpartners might be mediated by the additional dimensions predicted by string theory. The search for supersymmetric particles is, in a sense, a search for evidence of these extra dimensions. Physicists are hopeful that the Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator, will provide evidence for supersymmetry and the extra dimensions that string theory predicts. While no supersymmetric particles have been discovered yet, experiments at the LHC are ongoing, and every new experiment brings us closer to potentially confirming the existence of these hidden layers of reality. What these theories mean for our universe. Each of these theories, string theory, M theory, Kaluza-Klein theory, and supersymmetry, offers a different perspective on the nature of hidden dimensions. But they all point in the same direction. The universe may be much larger and more complex than we ever imagined. The extra dimensions predicted by these theories may be the key to understanding the deeper workings of the universe. For example, the mysterious force of dark matter, which makes up a significant portion of the universe's mass, could be explained by interactions with extra dimensions. According to some theories, dark matter particles might be able to move through these hidden dimensions, which would explain why we can't detect them through conventional methods. Similarly, the phenomenon of dark energy, the force that is causing the universe to accelerate its expansion, could also be influenced by the hidden dimensions. Some physicists suggest that dark energy could be the result of the gravitational effects of extra dimensions that we can't see but that still exert influence on our universe. These ideas are still in the realm of theoretical physics, and much more research is needed to test their validity. But the implications of these theories are profound. If extra dimensions exist, they could unlock a new understanding of the universe, bridging the gap between quantum mechanics, general relativity, and the forces that govern everything from the smallest particles to the largest structures in the cosmos. Hidden dimensions in action. Now that we've laid the theoretical groundwork for the existence of hidden dimensions, let's delve into the potential consequences of these extra dimensions. How might they manifest in the world around us? What implications could they have for the laws of physics, our understanding of the universe, and the forces we experience? In this section, we'll explore how these hidden dimensions might work in practice, and how scientists are attempting to detect them despite their elusiveness. Extra dimensions as a hidden layer. The idea of extra dimensions is a difficult one to grasp because they are not something we can directly perceive with our senses. Our everyday experiences are confined to the three spatial dimensions of length, width, and height, and one time dimension. The possibility of hidden dimensions beyond these familiar four dimensions is mind-boggling. However, the challenge of understanding them has not deterred physicists. It has, in fact, inspired a new way of thinking about the universe. So, what exactly could these extra dimensions look like? The simplest way to think about them is as compactified dimensions. Just as a garden hose can appear to be a one-dimensional line when viewed from a distance, but when examined closely reveals that it's actually a two-dimensional tube curled up, extra dimensions might be curled up at microscopic scales. These extra dimensions would not be directly observable, but their influence could still be felt, particularly on the behavior of fundamental forces like gravity and electromagnetism. A key concept here is the idea of hidden dimensions, which are thought to exist in a realm beyond our current understanding. These dimensions would have an immense impact on our reality, shaping how forces interact, how particles behave, and how matter is organized. The challenge is that we have no direct access to these dimensions in our everyday experiences, and they may be hidden from view by the sheer nature of their size or their ability to interact only through very specific conditions. The physics of extra dimensions, how laws of nature might change. If hidden dimensions exist, they would fundamentally alter the laws of physics. The forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force all interact within the familiar four dimensions of space-time. But in a universe with extra dimensions, these forces could behave quite differently. For instance, gravity might spread across multiple dimensions, which could explain why it is so weak compared to the other fundamental forces. In our three-dimensional world, gravity is incredibly weak. For example, the gravitational pull between two everyday objects is negligible compared to the electromagnetic force. But if gravity could access extra dimensions, it might be diluted as it leaks into them, making it appear weaker in the three dimensions we can observe. In string theory, these extra dimensions are thought to be tied to the various fundamental forces. The electromagnetic force, for example, may be an effect of the interactions within one of these extra dimensions. The stronger nuclear force and the weak nuclear force might also be tied to extra dimensions, potentially giving rise to new particles that we have yet to discover. The idea that extra dimensions influence the physical forces we observe raises several profound questions. Could we, in the future, develop the ability to manipulate these extra dimensions? Could we harness their influence to create new forms of technology, or even unlock the secrets of gravity? The possibilities are vast and awe-inspiring. How scientists are trying to detect hidden dimensions. Despite the challenges, scientists are actively seeking evidence for the existence of hidden dimensions. Some of the most promising ways to detect these extra dimensions involve indirect observations and high-energy physics experiments. In this section, we'll look at some of the ways in which scientists are trying to probe the fabric of the universe for signs of hidden dimensions. One of the primary ways scientists are looking for evidence of extra dimensions is through the use of particle accelerators, such as the Large Hadron Collider, LHC, at CERN in Switzerland. The LHC is capable of accelerating protons to nearly the speed of light and smashing them together to create conditions similar to those that existed in the early universe. By analyzing the particles produced in these collisions, scientists hope to find clues that point to the existence of extra dimensions. One specific way that extra dimensions might show up in these experiments is through the production of new particles. In the realm of string theory and M theory, the existence of extra dimensions could provide the necessary conditions for the creation of particles that are otherwise invisible in our three-dimensional world. These particles could manifest in the energy and momentum carried away from particle collisions. If new, unexpected particles are detected, it could be evidence of extra dimensions at play. Another method for detecting hidden dimensions involves the observation of gravitational waves. These ripples in space-time were first predicted by Albert Einstein and were directly detected for the first time in 2015 by the LIGO Observatory. Gravitational waves are caused by the acceleration of massive objects, such as merging black holes or neutron stars. But could gravitational waves also carry information from extra dimensions? In some theories, gravitational waves could be influenced by the presence of additional dimensions, causing them to behave in ways that differ from our current understanding. By studying the properties of these waves, scientists hope to uncover signs of hidden dimensions that might be interacting with the fabric of space-time. Finally, scientists are looking at cosmic background radiation, which is the afterglow of the Big Bang. This faint radiation permeates the entire universe, and its properties could offer valuable insights into the structure of the universe. The cosmic microwave background, CMB, might be affected by the presence of extra dimensions, leaving imprints that we can detect. Researchers are using increasingly sophisticated instruments to map the CMB in greater detail, hoping to find anomalies that might hint at the existence of hidden dimensions. The future of hidden dimensions. What lies ahead? Despite the challenges of directly detecting hidden dimensions, the pursuit is far from over. In fact, the next decade may bring significant breakthroughs in our understanding of these dimensions. The next generation particle accelerators could provide the energy needed to uncover new particles that hint at extra dimensions. Instruments like the James Webb Space Telescope and advanced gravitational wave observatories may also open new doors to detecting the fingerprints of hidden dimensions in the cosmos. The implications of discovering hidden dimensions would be monumental. It would not only revolutionize our understanding of the universe, but also have profound effects on the philosophy of science and our place in the cosmos. What if the very nature of reality is far stranger than we ever imagined? The discovery of hidden dimensions could fundamentally alter our understanding of space, time, and matter, and possibly even change how we perceive existence itself. In the coming years, as technology continues to advance and theoretical frameworks evolve, we may be on the brink of uncovering a secret layer of the universe that has been hidden in plain sight. If hidden dimensions do exist, they could hold the key to answering some of the most fundamental questions in physics, and perhaps unlock mysteries that have eluded us for centuries. The role of gravity, a glimpse into extra dimensions. Gravity, the weakest of the four fundamental forces in nature, is perhaps the most puzzling. It's a force we experience every day, pulling us toward the ground, shaping the orbits of planets, and even governing the motion of galaxies. Despite its omnipresence, gravity is significantly weaker than the other forces in nature, like electromagnetism or the strong nuclear force. But what if gravity's apparent weakness is a clue that leads to hidden dimensions? In this section, we'll explore the role gravity might play in the context of extra dimensions, how these dimensions could explain gravity's unusual properties, and what this means for the universe as we understand it. Gravity's weakness, a mystery in need of an explanation. The force of gravity is famously weak. For example, if you were to compare the gravitational force between two everyday objects, it would be negligible compared to the electromagnetic force. A simple example, the force of gravity between two protons is roughly 1036 times weaker than the electromagnetic force. This discrepancy has baffled scientists for centuries. In our everyday experience, we feel gravity's strength when we stand on the ground, when objects fall, or when we jump. But when we examine the fundamental forces of nature, gravity seems oddly out of place. The other three forces, electromagnetism, the strong nuclear force, and the weak nuclear force, all have much stronger effects at the atomic and subatomic levels. So, why is gravity so weak? Some physicists propose that the answer lies in the existence of extra dimensions. If gravity is not confined to just the three spatial dimensions we observe, it might spread across multiple dimensions, weakening its apparent force in the three dimensions we experience. This idea leads to the possibility that gravity could leak into extra dimensions, which would explain why it seems much weaker compared to the other forces. This theory is part of the large extra dimensions hypothesis, first proposed by physicist Nima Arkani Hamed in the late 1992. According to this theory, gravity's weakness in our familiar four-dimensional world could be the result of it being diluted by the existence of hidden, higher dimensional space. If this is true, It would mean that gravity behaves differently in the presence of extra dimensions, and we might need to reconsider the way we perceive its force. Gravity and the extra dimensions, theoretical models. There are several models in modern physics that attempt to explain gravity's weakness by invoking the existence of extra dimensions. One of the most influential models is Randall-Sundrum theory, proposed by physicists Lisa Randall and Raman Sundrum. In their theory, they suggest that the universe consists of two branes, higher dimensional objects, embedded in a higher dimensional space. Our observable universe exists on one brane, and the gravitational force is confined to that brane. However, gravity could spread across the entire higher dimensional space, effectively diluting its strength in our four-dimensional world. This theory suggests that the true nature of gravity is not confined to the four-dimensional space-time we experience, but instead, it can leak into higher dimensional spaces. This leakage would explain why gravity is much weaker compared to other forces. In other words, if gravity is allowed to spread out over multiple dimensions, it would appear weaker in our three-dimensional world. Another important theory that explains gravity's weakness is string theory, particularly the idea that gravity interacts with multiple spatial dimensions. In string theory, the fundamental particles of nature, including the gravitum, the hypothetical particle that mediates the force of gravity, are thought to vibrate in multiple dimensions. These extra dimensions provide the space for gravity to spread out, weakening its influence in the familiar four-dimensional world. In this model, gravity is not just a force operating in three dimensions, but is part of a larger, multi-dimensional framework. Gravitational waves, a possible detection of extra dimensions. In recent years, scientists have begun to study gravitational waves, ripples in the fabric of space-time caused by massive objects like merging black holes or neutron stars. These waves were first predicted by Albert Einstein in 1915 as part of his theory of general relativity, but it wasn't until 2015 that they were directly detected by the LIGO Laser Interferometer Gravitational Wave Observatory. Gravitational waves are an exciting area of study because they provide a new way to observe the universe. Unlike light, which can be blocked or scattered by matter, gravitational waves travel through the universe without distortion. This means they can carry information from distant regions of space, potentially providing clues about hidden dimensions. Some theories suggest that gravitational waves could be influenced by the existence of extra dimensions. If higher dimensions exist, they could affect the propagation of gravitational waves, causing them to behave differently than we would expect in a four-dimensional world. For example, gravitational waves might interact with additional dimensions in ways that cause them to dissipate or change their properties as they travel through space. By studying the characteristics of these waves, scientists could potentially detect signs of extra dimensions. At the moment, gravitational waves are being studied to explore the nature of black holes, neutron stars, and the early universe. However, future experiments with more advanced detectors could potentially reveal clues about the existence of hidden dimensions. As our ability to detect and analyze gravitational waves improves, we may find that they hold the key to unlocking the mysteries of extra dimensions. The Large Hadron Collider. Probing for extra dimensions. The Large Hadron Collider, LHC, located at CERN, is the world's largest and most powerful particle accelerator. It's designed to smash protons together at nearly the speed of light, recreating the conditions that existed just after the Big Bang. These collisions produce a shower of particles, which are then analyzed by scientists to understand the fundamental forces and particles that make up the universe. One of the primary goals of the LHC is to search for evidence of new physics, including the existence of extra dimensions. The idea is that, in the high-energy collisions produced by the LHC, particles might exhibit behavior that suggests they are interacting with extra dimensions. In particular, the LHC might be able to detect the production of microscopic black holes. These black holes would be tiny, on the scale of subatomic particles, and would only exist for a fraction of a second. However, their creation could provide evidence that the LHC is probing extra dimensions. If these black holes are produced, it would suggest that gravity is interacting with higher dimensional space, as predicted by theories like Randall-Sundrum. Detecting these black holes would be a groundbreaking discovery, as it would provide the first concrete evidence for the existence of extra dimensions. However, this is still a highly speculative area of research, and scientists are continuing to analyze data from the LHC to look for any signs of these elusive particles or phenomena. The future of gravity and extra dimensions. As we continue to explore the mysteries of gravity and extra dimensions, the potential for groundbreaking discoveries is immense. Theoretical physicists are developing new models that attempt to unify gravity with the other fundamental forces, and experimental physicists are working tirelessly to detect the elusive signatures of extra dimensions. If we can unlock the secrets of gravity's weakness, we could revolutionize our understanding of space, time, and the forces that govern the universe. New technologies, such as more powerful particle accelerators and gravitational wave detectors, could provide the tools we need to detect these hidden dimensions and explore the true nature of the cosmos. In the next section, we'll dive into how extra dimensions might help explain some of the most perplexing phenomena in the universe: dark matter and dark energy. These mysterious forces have confounded scientists for decades, and extra dimensions could provide the missing piece of the puzzle: dark matter and dark energy, the hidden forces of the universe. As we venture deeper into the enigma of hidden dimensions, one of the most profound questions that arises is whether these dimensions could help explain two of the greatest mysteries in modern physics: dark matter and dark energy. These elusive forces make up a vast majority of the universe's mass and energy, yet we cannot directly observe them. They don't emit, absorb, or reflect light, making them nearly invisible to our current scientific tools. However, their effects are felt across the cosmos, influencing the behavior of galaxies, stars, and even the expansion of the universe itself. Could hidden dimensions be the key to unlocking the secrets of dark matter and dark energy? In this section, we'll explore these two cosmic phenomena and how they might be connected to the extra dimensions beyond our perception. Dark matter, the invisible mass of the universe. The universe, as we know it, is made up of atoms, stars, planets, and galaxies. However, scientists have long realized that visible matter, the matter that emits light and other forms of radiation, accounts for only a small fraction of the total mass in the universe. Observations of galaxies and galaxy clusters have revealed that there is far more mass present than we can detect with traditional methods. This missing mass is known as dark matter. Dark matter was first proposed by astronomer Fritz Zwicky in the 1930 seconds, when he noticed that the galaxies in galaxy clusters were moving much faster than expected based on the visible matter alone. He suggested that there must be some unseen mass exerting a gravitational pull, keeping these galaxies from flying apart. Since then, astronomers have gathered substantial evidence for the existence of dark matter, including its effects on the rotation of galaxies and gravitational lensing, where light from distant objects is bent by the gravitational influence of dark matter. Despite its gravitational effects, dark matter does not interact with electromagnetic radiation. It neither emits nor absorbs light, which is why it remains invisible to our current instruments. This has made dark matter incredibly difficult to detect directly, and scientists have spent decades searching for its true nature. But could hidden dimensions provide a clue to understanding dark matter? Some theories suggest that dark matter might not be composed of traditional particles that we can observe directly, but rather could involve particles that interact with extra dimensions. According to string theory, particles that interact in higher dimensional spaces could produce forces or particles that we cannot observe in our three-dimensional world. One such theory is that dark matter consists of WIMPs, weakly interacting massive particles, which are theorized to be heavy particles that only interact via gravity and the weak nuclear force. These particles could exist in a higher dimensional space and may only interact with our universe through gravitational forces or possibly through the exchange of particles that we have yet to detect. Additionally, dark matter could be the result of gravitons, the hypothetical particles that mediate gravity, interacting with the extra dimensions. If these gravitons are not confined to the three-dimensional space we experience, they could interact with higher dimensions, creating effects that manifest as dark matter in our universe. The search for dark matter continues through experiments such as those conducted in underground labs, particle accelerators, and cosmic observations. If scientists can detect the elusive particles that make up dark matter, it could provide direct evidence for the existence of extra dimensions and revolutionize our understanding of the universe. Dark energy, the mysterious force behind the universe's expansion. If dark matter represents the invisible mass that holds galaxies, together, dark energy is the mysterious force that is driving the expansion of the universe. For most of the 20th century, scientists believed that the universe's expansion was slowing down due to gravity, the force that pulls matter together. However, in the late 1992, two independent teams of astronomers discovered something startling. The expansion of the universe is actually accelerating. This discovery was based on observations of distant Type Ia supernovae exploding stars that are used as standard candles to measure distances in the universe. The surprising result was that these supernovae were farther away than expected, implying that the universe had been expanding at an accelerating rate over the past several billion years. This accelerated expansion is attributed to a mysterious force called dark energy, which makes up about 68% of the total energy content of the universe. Like dark matter, dark energy does not emit light or any form of detectable radiation, making it virtually invisible. Yet, its presence is felt in the very fabric of the universe, driving galaxies apart and accelerating the expansion of space-time itself. Dark energy's exact nature remains one of the greatest unsolved mysteries in physics. However, some theories suggest that dark energy could be linked to the properties of extra dimensions. In particular, the idea that the universe's accelerated expansion could be driven by the interaction between our universe and higher dimensional space is an intriguing possibility. One theory that connects dark energy with hidden dimensions comes from string theory. In some models, the vacuum energy, the energy that fills empty space, could be influenced by the geometry of extra dimensions. In this context, dark energy might be the manifestation of forces or interactions in these higher dimensional spaces that we cannot observe directly. The energy associated with these interactions could cause the observed acceleration of the universe's expansion. Another possibility comes from brain cosmology, a branch of M theory, which suggests that our universe might be a three-dimensional brain embedded in a higher dimensional space. In this model, the expansion of the universe could be driven by the interactions between our brain and the higher dimensional space in which it resides. The energy from these interactions could manifest as dark energy, accelerating the expansion of the universe, connecting dark matter, dark energy, and extra dimensions. The connection between dark matter, dark energy, and hidden dimensions is still a topic of active research, but these theories offer a tantalizing possibility. If extra dimensions exist, they could provide the framework needed to understand both dark matter and dark energy. For instance, dark matter could be explained by particles that interact with higher dimensions, while dark energy could arise from the energy in these extra dimensions influencing the fabric of space-time. One promising avenue for exploring these connections is experimental cosmology, which aims to map the properties of dark matter and dark energy by studying their effects on the large-scale structure of the universe. This includes observing the distribution of galaxies, the cosmic microwave background radiation, and gravitational lensing. By analyzing these phenomena, scientists hope to find clues about the role of hidden dimensions in the behavior of dark matter and dark energy. In the future, as our understanding of extra dimensions improves, we may find that dark matter and dark energy are not separate mysteries, but two sides of the same coin, both shaped by the hidden dimensions that underlie the fabric of the universe. The implications for the standard model of physics. The discovery of a connection between extra dimensions, dark matter, and dark energy would have profound implications for the standard model of particle physics, the current framework that describes the fundamental particles and forces of the universe, except for gravity. The Standard Model has been incredibly successful in explaining most phenomena in particle physics, but it does not account for gravity, dark matter, or dark energy. If extra dimensions are indeed a part of our reality, they would provide the missing pieces needed to complete the Standard Model and unify gravity with the other fundamental forces. The inclusion of higher dimensions could bridge the gap between quantum mechanics and general relativity, the two pillars of modern physics that currently operate in separate realms. This would be a monumental breakthrough, bringing us one step closer to a theory of everything, a unified theory that explains all the forces of nature within a single framework. The multiverse. Is our universe just one among many? As we've explored, the notion of hidden dimensions is not merely a theoretical curiosity, but a cornerstone of some of the most promising ideas in modern physics. From explaining gravity's weakness to shedding light on the elusive dark matter and dark energy, these extra dimensions could transform our understanding of the universe. But the implications of these dimensions go even further. Could they be the key to understanding the very nature of existence itself? Could hidden dimensions allow for the existence of parallel universes, leading to the mind-bending concept of a multiverse? In this section, we will delve into the idea that hidden dimensions could give rise to multiple universes, each with its own laws of physics, constants, and perhaps even realities that are completely different from ours. We'll explore the scientific and philosophical implications of the multiverse theory, how it relates to hidden dimensions, and what it means for the future of our understanding of the cosmos. The concept of the multiverse. The multiverse is the idea that our universe, the one we observe, study, and experience, may not be the only one. Instead, there could be an infinite number of universes, each with its own set of physical laws and constants. These universes could range from being strikingly similar to ours to being radically different in terms of the fundamental forces, particles, and even the dimensions that govern them. The idea of a multiverse isn't new, but it has gained significant attention in modern physics, especially in the context of string theory and M-theory, which propose the existence of extra dimensions. According to these theories, our universe might be just one of many branes, higher dimensional objects that exist in a larger, multidimensional space. These branes could be parallel to each other, each hosting its own universe. In this way, the multiverse could be made up of a collection of parallel universes that are all part of a higher dimensional space. The concept of a multiverse challenges our traditional understanding of the universe and reality itself. In the classical view, our universe is all there is, everything that exists, from galaxies to atoms, resides within this single framework. However, the idea of the multiverse suggests that our universe is merely one among many, each with its own distinct properties. In this view, the cosmos becomes far more complex and infinitely larger than we could have imagined. Extra dimensions and the multiverse, how they connect. The connection between extra dimensions and the multiverse is deeply rooted in the mathematical foundations of string theory and M-theory. In these theories, the existence of hidden dimensions isn't just a theoretical necessity, it's a feature of the universe that could allow for the formation of multiple, parallel universes. In string theory, the extra dimensions we've discussed are not just extras, they are integral to the very fabric of reality. String theory proposes that fundamental particles are not point-like objects, but tiny vibrating strings. These strings exist in higher dimensional space, and the way these strings vibrate determines the properties of the particles they create. The dimensions beyond our familiar 4-3 of space and 1 of time could allow for the existence of multiple, distinct universes, each with its own set of physical properties. The idea is that our universe might be confined to one brane within a higher dimensional space, and other branes, universes, could exist parallel to ours, with their own distinct laws of physics. These universes might never interact, or they might occasionally collide or influence one another. The multiverse could be a vast collection of such branes, each a separate universe, with the extra dimensions providing the space for them to coexist. In M-theory, a more general framework that extends string theory, the number of dimensions is even higher. It suggests that there could be up to 11 dimensions in total. In this framework, our universe could be just one of many that exist within this higher dimensional space, each with its own set of dimensions, properties, and even physical laws. The idea of a multiverse in this context is not just theoretical but a natural consequence of the structure of M-theory. Implications for our understanding of reality. The implications of the multiverse theory are profound. If multiple universes exist, it raises questions about the nature of reality itself. How do we define what's real if there are an infinite number of realities, each with its own set of rules? Could there be universes where the laws of physics are completely different from ours, where time runs backward, or where gravity doesn't exist? And if so, how would that affect our understanding of everything we know, from the beginning of the universe to the fundamental forces of nature? One of the most mind-boggling implications of the multiverse is the possibility of alternate versions of ourselves. In a multiverse, there could be universes that are almost identical to ours, with only subtle differences. In some of these universes, we might have made different decisions, leading to alternate versions of our lives. This idea is reminiscent of the many worlds interpretation of quantum mechanics, which suggests that every time a quantum event occurs, the universe splits, creating parallel realities in which different outcomes occur. While this concept sounds like science fiction, some physicists argue that it could be a legitimate consequence of the multiverse theory. If there are infinite universes, each with its own set of initial conditions, then it is possible that in some of them, events unfold in ways that are radically different from what we experience. This leads to a fascinating idea. The multiverse could be a place where every possibility, no matter how improbable, is realized somewhere. Scientific and philosophical reactions to the multiverse. The idea of a multiverse is not without its critics. One of the main objections to the theory is that, if there are indeed infinite universes, we may never be able to observe or test them. In science, the hallmark of a good theory is that it is testable and falsifiable, that is, there must be a way to prove whether the theory is correct or wrong. However, the multiverse theory raises a problem. If other universes are completely separate from our own, we may never be able to observe them directly. This raises the question of whether the multiverse is a scientifically valid concept at all. Philosophically, the multiverse challenges our understanding of existence and reality. If there are infinite versions of ourselves, with infinite possibilities unfolding in parallel universes, what does that mean for the choices we make and the meaning of our lives? Are we simply one of many versions of ourselves, living out one of countless possible realities? Despite these philosophical challenges, many physicists and cosmologists see the multiverse theory as a natural extension of the principles of physics. The multiverse is a theoretical consequence of certain models of cosmology and quantum mechanics, and it is supported by mathematical equations derived from these theories. For some, the multiverse is not just a speculative idea, but a testable prediction that could one day be confirmed or refuted by scientific observation. Testing the multiverse. Can we prove its existence? The question remains, how can we test the multiverse theory? Since the multiverse suggests the existence of parallel universes that are separate from ours, finding direct evidence of these universes could be challenging, if not impossible. However, there are some indirect ways scientists are attempting to test the multiverse hypothesis. One promising approach involves studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Some versions of the multiverse theory suggest that our universe might have collided with other universes in the distant past, and these collisions could leave imprints on the CMB. If we detect unusual patterns or anomalies in the CMB, it could provide indirect evidence of the multiverse. Another possible avenue of testing is the study of cosmic inflation, a rapid expansion of space that occurred in the early moments of the universe. Some models of inflation suggest that it could lead to the creation of multiple, independent universes. By studying the properties of inflation in greater detail, scientists might be able to uncover clues that point to the existence of a multiverse. The future of physics and the search for hidden dimensions. As we stand at the frontier of modern physics, the search for hidden dimensions continues to be one of the most exciting and transformative areas of research. Theoretical advancements, combined with increasingly sophisticated technology, promise to reveal more about the hidden nature of our universe. In this section, we will explore the future of physics as it relates to hidden dimensions, the next steps in experimental research, and the potential breakthroughs that could reshape our understanding of reality. We'll also discuss the far-reaching implications these discoveries could have on science, technology, and even philosophy. The next frontier in physics. Physics is entering an era of rapid advancements. With the rise of quantum computing, particle accelerators, and gravitational wave detectors, the tools available to scientists have never been more powerful. These innovations are pushing the boundaries of what we can observe and test, enabling us to explore deeper into the very fabric of the universe. Hidden dimensions are at the heart of this exploration, and while we have yet to uncover definitive proof, the progress being made provides tantalizing hints that we might be closer than ever to making groundbreaking discoveries. One of the most pressing questions for physicists is how to unify the two pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics, which governs the behavior of particles on the smallest scales, and general relativity, which describes gravity and large-scale phenomena, are both incredibly successful in their respective domains. However, these two theories do not mesh well when it comes to extreme environments, such as black holes or the early universe. Extra dimensions may provide the key to reconciling these two theories. String theory and M theory, which involve the existence of hidden dimensions, offer potential solutions to this conflict. In these frameworks, gravity is not a force confined to the four-dimensional space-time we experience, but rather one that is mediated through higher dimensional spaces. By better understanding the mathematics of these theories, physicists hope to derive a more complete theory of quantum gravity, one that accounts for both the quantum and relativistic realms. Technological advances, paving the way for new discoveries. The hunt for hidden dimensions is closely tied to technological advancements in several fields. High-energy particle accelerators, gravitational wave observatories, and space telescopes are some of the key instruments driving the search for extra dimensions. Let's take a look at how these technologies are paving the way for new discoveries. Particle accelerators, pushing the boundaries of the microcosm. Particle accelerators, such as the Large Hadron Collider, LHC, at CERN, have already provided extraordinary insights into the universe. The LHC has been instrumental in the discovery of the Higgs boson, a particle that was predicted by the standard model of particle physics, but had eluded detection for decades. The LHC smashes particles together at near-light speeds, creating conditions similar to those just after the Big Bang. These collisions produce a wealth of new particles, and by analyzing their behavior, scientists can learn about the fundamental forces and particles of the universe. As the LHC and other particle accelerators continue to evolve, they may offer us the opportunity to directly observe signs of extra dimensions. One of the key predictions of string theory is that microscopic black holes could be produced in high-energy particle collisions. These black holes would be incredibly small and would only exist for a fraction of a second, but their detection would provide the first concrete evidence of extra dimensions. If the LHC or future particle accelerators can detect such black holes, it would revolutionize our understanding of the universe and confirm the existence of higher dimensional spaces. Gravitational wave detectors, listening to the fabric of space-time. Gravitational waves, which were first detected in 2015 by the LIGO Laser Interferometer Gravitational Wave Observatory collaboration, have opened a new window into the universe. These ripples in space-time are caused by massive objects like black holes or neutron stars colliding and merging. Gravitational waves travel through the universe, carrying information about their origins and the nature of space-time itself. Some theories suggest that hidden dimensions could affect the propagation of gravitational waves. In particular, the presence of extra dimensions might cause gravitational waves to behave differently from our expectations. By studying the properties of these waves, scientists may be able to detect signatures of higher dimensional space. For example, gravitational waves could carry information about the geometry of extra dimensions, revealing their influence on the structure of space-time. Future improvements to gravitational wave observatories, like LIGO and the upcoming LISA, Laser Interferometer Space Antenna, will allow for even more precise measurements, potentially bringing us closer to detecting extra dimensions. Space telescopes, mapping the cosmos for hidden signatures. Space-based telescopes, such as the James Webb Space Telescope, JWST, are poised to revolutionize our understanding of the universe. These telescopes are capable of observing the most distant and faintest objects in the cosmos, from distant galaxies to the first stars that formed after the Big Bang. In addition to providing insights into the origins and evolution of the universe, these telescopes could help detect the effects of hidden dimensions on large-scale structures in space. One potential way to detect the influence of extra dimensions is by studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB carries vital information about the early universe, and some models of the multiverse suggest that our universe may have collided with other universes in the past. Such collisions could leave imprints on the CMB, creating anomalies or patterns that would be consistent with the presence of extra dimensions. Space telescopes like the JWST, with their advanced imaging, spectroscopic capabilities, could help identify these imprints, providing further evidence for the existence of hidden dimensions. The impact on humanity, a new view of reality. The discovery of hidden dimensions would be nothing short of revolutionary. It would not only change our understanding of physics and the cosmos, but also have profound philosophical, technological, and cultural implications. Imagine a world where the fundamental nature of reality is no longer constrained by the 4 dimensions we experience. How would our understanding of space, time, and matter change? For one, it would force us to rethink the concept of reality itself. If there are extra dimensions that we cannot perceive directly, it suggests that the universe is far more complex than we have ever imagined. Our understanding of existence, and even of ourselves, could be radically altered. The implications for philosophy, metaphysics, and even spirituality could be profound. What does it mean for us to live in a universe that is part of a vast, multidimensional reality, potentially with infinite parallel universes? On a more practical level, the discovery of hidden dimensions could lead to new technologies that we can hardly imagine today. For example, if we could find a way to interact with extra dimensions, it might allow for new forms of energy, advanced materials, or even new methods of communication. We could unlock the mysteries of gravity and quantum mechanics, potentially creating breakthroughs in everything from energy generation to space travel. The ability to manipulate higher dimensional spaces could also open up entirely new avenues for computing and information storage, potentially leading to technologies far beyond what we currently conceive. Challenges and the road ahead. Despite the exciting potential, there are significant challenges to detecting and understanding hidden dimensions. The most obvious challenge is the indirect nature of extra dimensions. They are not something we can simply observe directly. The evidence for their existence comes from the subtle effects they have on the universe, whether in the behavior of fundamental forces, the properties of particles, or the geometry of space-time itself. Detecting these effects requires an extraordinary level of precision and the development of new experimental methods. Another challenge is the theoretical complexity of these ideas. String theory, M theory, and other models involving extra dimensions are highly abstract and mathematically complex. The mathematics required to describe these higher dimensional spaces is incredibly intricate, and testing these theories in the laboratory remains a formidable task. Theoretical physicists will need to continue refining their models and hypotheses to make them more testable and verifiable. Despite these challenges, the search for hidden dimensions remains one of the most exciting frontiers in science. As new technologies and experimental methods continue to emerge, we may one day uncover the elusive secrets of extra dimensions and unlock a new understanding of the universe that changes everything we know. Conclusion: the infinite possibilities of the universe. As we come to the end of this journey through the hidden dimensions of the universe, one thing becomes abundantly clear. Our understanding of reality is still in its infancy. Theories of extra dimensions, hidden layers of space-time, and parallel universes not only challenge the very foundations of physics, but also invite us to think beyond the limitations of our own perception. We are on the cusp of potentially reshaping everything we know about the cosmos, from the forces that govern it to the very nature of existence itself. In this final section, we'll take a step back and reflect on the vast potential of the discoveries we've explored, consider how they might alter our future, and end with a final thought that invites us to contemplate the profound mysteries still waiting to be uncovered. Recap of our journey. Throughout this exploration, we have seen how hidden dimensions could provide the answers to some of the universe's most perplexing mysteries. From gravity's weakness to the nature of dark matter and dark energy, extra dimensions offer a potential explanation for the forces and phenomena that we can observe but not fully understand. String theory and M theory, Kaluza-Klein theory, and supersymmetry all hint at a reality far more complex than our familiar three-dimensional world. We've also explored the possibility of a multiverse, where our universe is not an isolated system but one of many, each with its own set of laws, particles, and dimensions. This concept opens up a radically new way of thinking about existence, suggesting that reality may be far stranger and more varied than we can imagine. In the realm of experimental physics, we've discussed how technologies like the Large Hadron Collider, gravitational wave detectors, and space telescopes like the James Webb Space Telescope are bringing us closer to uncovering hidden dimensions. Though the road to discovery is long, the potential breakthroughs are immense, and they promise to radically alter our understanding of the cosmos. The endless possibilities of hidden dimensions. The exploration of hidden dimensions is far from a trivial pursuit. It is, in many ways, a quest to understand the very fabric of reality itself. As physicists work to understand how extra dimensions might work, they are not just attempting to solve abstract mathematical puzzles, they are seeking to answer some of the most fundamental questions about the universe. Why is gravity so weak compared to other forces? What is the true nature of dark matter and dark energy? Is our universe just one of many? And if so, what does that mean for the nature of existence? How do the laws of physics behave in higher dimensional spaces? And what implications does that have for the future of technology, energy, and space travel? The answers to these questions could revolutionize not just physics, but the very way we view the world. For example, the discovery of extra dimensions could lead to a new understanding of gravity, one that could provide breakthroughs in energy production, computing, or even transportation. If we can tap into the mysteries of higher dimensional space, we could unlock entirely new technologies that seem like science fiction today. Concepts like warp drives, quantum computing, and unified field theories could all be brought into reality. Beyond the practical applications, the idea of hidden dimensions also has profound philosophical implications. If our universe is just one of many, what does that mean for our place in the cosmos? Are we just one version of reality among countless others? What does it mean for our identity and our understanding of existence if parallel universes, with their own histories, choices, are out there? These questions blur the lines between science, philosophy, and metaphysics, leading to a richer, more complex view of the universe. The ongoing quest for knowledge. As we've seen, the search for hidden dimensions is still in its early stages. Much of the theoretical work remains speculative, and we have yet to find direct experimental evidence that confirms the existence of these extra dimensions. However, the theoretical framework is strong, and there is increasing confidence that these dimensions are not just mathematical artifacts, but real features of the universe that could one day be detected. The future of physics is poised to tackle these challenges head-on, with quantum computers on the horizon and ever more powerful particle accelerators. We may soon have the tools to peer deeper into the fabric of space-time than ever before. The study of gravitational waves, dark matter, and dark energy could reveal the hidden layers of the cosmos, providing clues about the existence of dimensions beyond space and time. The next few decades may bring discoveries that will transform our understanding of the universe in ways we can scarcely imagine. The quest for hidden dimensions is not just a scientific endeavor, but a deeply human one. It is a pursuit driven by curiosity, wonder, and a desire to understand our place in the vast, mysterious universe. Final thought: shattering the illusion of reality. The exploration of hidden dimensions forces us to confront an uncomfortable but exhilarating idea. What we perceive as reality is only a fraction of the total picture. Our experience of the universe is limited by our senses, our technologies, and the constraints of our three-dimensional existence. But what if this reality is just a thin veil, hiding a much richer, more complex world beneath the surface? In the grand scheme of the cosmos, the dimensions we experience may be just a tiny sliver of a vast, multi-dimensional reality that governs everything. If hidden dimensions truly exist, they offer a glimpse into a universe far stranger and more wondrous than we have ever imagined. As we look toward the future, The discovery of these dimensions may change everything we know about physics, about existence, and about the very nature of the universe. It is a reminder that the pursuit of knowledge is a journey without end, and every answer we uncover leads to even more profound questions. The universe is vast, and the possibilities are truly infinite. So, the next time you look up at the night sky or ponder the mysteries of the universe, remember that the reality we perceive is only one layer of a far more complex and enigmatic existence. Hidden dimensions may be waiting for us to discover them, and when we do, they will reveal a universe far beyond our wildest imagination.